In 1967, Mordell revisited the equation a fourth power plus m times another fourth power equals a square in the Quarterly Journal of Mathematics, sharpening earlier results of Pocklington, Nagell, and Lind. He identified several cases for which non-trivial integer solutions are impossible. Many of them can be proven by a simple application of infinite descent. Among these are the equations with m prime, the positive sign case p is congruent to 7 and 11 modulo 16, and the negative sign case p is congruent to 3, 11, and 13 modulo 16. Unfortunately, Mordell's paper sits behind the paywall, so we cannot directly see how he applied infinite descent. The good news is that we can reconstruct his arguments using nothing more than congruences, careful coprimality analysis, suitable factorizations, and infinite descent. We assume a primitive minimal solution and split the proof according to parity of x, y, and z. First, suppose x is even while y and z are odd. A straightforward congruence calculation, modulo 16, forces p to lie in only two residue classes, 1 and 9 modulo 16. Therefore, the classes 3, 5, 7, 11, 13, and 15 are excluded. Next, suppose x and y are odd while z is even. Reducing the equation, modulo 16 again leaves only two possibilities, 3 and 15 modulo 16. So the classes 1, 5, 7, 11, and 13 are ruled out. Finally, suppose x and z are odd while y is even. In this case, the congruence analysis becomes inconclusive. Modulo 16, the equation imposes no restriction on p. So this parity structure requires an infinite descent argument. The table below summarizes the findings so far, showing that the classes 5 and 13 modulo 16 must remain possible within the descent argument in order to match Mordell's result. So we are in the case with x and z odd and y even. We first write y as 2w, then we factor, knowing that 16 divides the product. Thus, 8 divides one factor and 2 the other, or 4 divides each factor. This second case can be ruled out since 4 should divide the difference, which clearly doesn't since x is odd. Next, after dividing by 2, the factors are coprime. Therefore, they must be either a fourth power or p times a fourth power. We have two cases to analyze. The first case gives a raised to the fourth minus 4 times b raised to the fourth equals plus minus x squared. The negative sign can be discarded with a simple modulo 4 argument. So we have a raised to the fourth minus 4 times b raised to the fourth equals x squared, and z equals a raised to the fourth plus 4 times b raised to the fourth. Next, we factor this equation, and since a and x are odd, each factor is divisible by 2. Using coprimality again, each factor must take the form of twice a fourth power or twice p times a fourth power. Adding gives a squared equals u raised to the fourth plus p times v raised to the fourth. Note that if b were odd, then a, u, and v would be odd. Impossible. So b is even and u and v are of opposite parity. If u is odd and v is even, we obtain an equation of the same shape and parity structure as the original, but of smaller magnitude. Squared is smaller than z squared, producing a descent for every residue classes of p modulo 16. If u is even and v is odd, it's the same case we already discussed, where classes 3, 5, 7, 11, 13, and 15 modulo 16 are ruled out. Now we move to case 2. Subtracting the equation yields p times a raised to the fourth minus 4 times b raised to the fourth equal plus minus x squared. Since x is odd, a cannot be even, and for a odd, p is congruent to plus minus 1 modulo 4. In the positive sign case, p is congruent to 1 modulo 4. Hence, this excludes classes 3, 7, 11, and 15. In the negative sign case, p is congruent to minus 1 modulo 4. This already rules out classes 1, 5, 9, and 13. but we can sharpen further the argument. We first factor, and since A, X, and P are odd, the factors are odd as well. A simple coprimality analysis shows that these factors are coprime. So each one is either a fourth power or P times a fourth power. Adding the equation gives the square of 2b equals u raised to the fourth plus p times v raised to the fourth, an equation of the same form as the original but of smaller magnitude, producing a descent for p equal or bigger than 5. However, u and v are odd while 2b is even, so the descended solution has a different parity structure. Nevertheless, this is precisely the parity class already analyzed, where only P congruent to 3 and 15 remain possible, ruling out the classes 1, 5, 7, 11, and 13. Summing up the findings in both paragraphs, subcase 2 exclude classes 1, 5, 7, 9, 11, and 13. Summing up, the first table analyzed the three possible parity structures using congruences modulo 16. The first two cases were resolved purely by congruence arguments, while the third case remained inconclusive, forcing us to use infinite descent. Notice that the overlap of the first two cases already rules out the residue classes 7 and 11 modulo 16, exactly as in Mordell's results. However, those arguments also leave the classes 5 and 13 still possible. So the descent argument must preserve these two classes if we want to recover Mordell's final results correctly. This is why the second table focuses entirely on the third parity structure. There, among all the branches, the crucial one is case 2 subcase 1, with a positive sign, because it is the only branch compatible with the classes 5 and 13. Combining the congruence analysis with the descent argument, we finally recover Mordell's result. The equation admits no non-trivial integer solutions when P is congruent to 7 or 11 modulo 16. In this table, we display the primitive non-trivial solutions for the first primes congruent to 3 and 15 modulo 16. Note, all solutions have x and y odd while c even, except the first case. 1 raised to the fourth plus 3 times 2 raised to the fourth equals 7 squared, which can be recovered by descent. We will now recover this case by descent. Because the associated form admits unique factorization, we can instead exploit a parametrization argument. As usual, assume a minimal solution with x, y, and z coprime. We can parameterize x squared, y squared, and z this way with a and b coprime and of opposite parity. Next, we see that the first equation has the same shape as we are working with. So x squared plus 3 times v squared equals a square also admits parametrization. This time, the parametrization uses variables u and v odd, so it has slightly a different form. Substituting gives y squared equals u times v times u squared plus 3 times v squared. So here we have to consider two cases. If 3 doesn't divide u times v, then each factor must be a square. Substituting yields u sub 1 raised to the fourth plus 3 times v sub 1 raised to the fourth equals y sub 1 squared, of the same shape as the original equation, but smaller since y sub 1 squared is smaller than y raised to the fourth, which is smaller than z squared. Its only trivial solution is u sub 1 equals v sub 1 equals 1 and y sub 1 equals 2. Hence, u equals v equals 1, so y equals 2, b equals 1, a equals 2, x equals minus 1, and z equals 7. Thus, we recover 1 plus 3 times 2 raised to the fourth equals 7 squared. The branch where 3 divides u times v also leads to a descent. The case v divisible by 3 yields a contradiction, while u divided by 3 recovers only this scaled solution. Now we study the equation x raised to the fourth minus p times y raised to the fourth equals a square. And we want to show that there are no non-trivial solutions for several residue classes of P modulo 16. As before, we assume a primitive minimal solution and split the proof according to the parity of the variables. First, we look the case x even while y and z odd. Looking modulo 16, P congruent to 7 and 15 are possible, while the classes 1, 3, 5, 9, 11, and 13 are excluded. Next, we analyze the case x and y odd while z even. Again, working modulo 16, we find that only two residue classes remain possible for P, 1 and 13, excluding the classes 3, 5, 7, 9, 11, and 15. Since the class 13 must also be ruled out to match Mordell's result, we dig a little further. We factor the equation as x squared minus z times x squared plus z. A coprimality analysis shows that these factors are coprime, so one must be a fourth power and the other p times a fourth power. Adding gives 2x squared equals a raised to the fourth plus p times b raised to the fourth. Since x squared is congruent to 1 and 9 modulo 16, it follows that 2x squared is congruent to 2 modulo 16. And because a and b are odd, then the left-hand side is congruent to 1 plus p. Thus, p is congruent to 1 modulo 16. This excludes the classes 3, 5, 7, 9, 11, 13, and 15, ruling out the class 13 as required. Summing up, to recover Mordell's result, we must exclude residue classes 3, 11, and 13, modulo 16, while retaining 5 and 9. For the final parity case, we take x and z odd while y is even. So we write y as 2w and factor the equation into the product of two terms, which is divisible by 16. Thus, either 8 divides one factor and 2 the other factor, or 4 divides each factor. This second case can be ruled out since 4 should divide the sum, which clearly doesn't since x is odd. Thus, we have the 2 divides one of the factors and 8 the other. Since x and z are coprime, then the factors divided by 2 are coprime too, as follows from the sum and difference. Therefore, the factors must be either a fourth power or p times a fourth power. So we have to analyze two cases. Case 1. Adding the equation gives a raised to the fourth plus 4 times p times b raised to the fourth equals x squared. Since x is odd, then a must be odd. Rearranging this plus dividing by 4 gives that p times b raised to the fourth equals x minus a squared over 2 times x plus a squared over 2. These factors are coprime. Hence, each factor is either a fourth power or p times a fourth power. Subtracting them gives u raised to the fourth minus p times v raised to the fourth equals plus minus a squared. As a is odd, u and v must have opposite parity. The positive sign case gives u raised to the fourth minus p times b raised to the fourth equals a squared, yielding an equation of the same shape as the original, but of smaller square parameter, since a squared is smaller than x squared, hence producing a descent. When the parity structure is u odd and v even, it matches the case under analysis. Thus, the descent applies to all classes, allowing to rule out them all. But when the parity structure is u even and v odd, we are back to case x even and y odd previously analyzed, where classes 1, 3, 5, 9, 11, and 13 are excluded. Thus, the plus sign case rules out the residue classes 1, 3, 5, 9, 11, and 13 modulo 16. The negative sign case gives u raised to the fourth plus a squared equals p times v raised to the fourth. Since u and v are coprime, it follows that u, a, and p are also coprime. Hence, p divides a sum of two coprime squares, so p must be of the form 4n plus 1. Therefore, the classes 3, 7, 11, and 15 are excluded. But we can push the analysis further on the remaining classes 1, 5, 9, and 13. Since a is odd, then u and v have opposite parity. If u is odd and v even, then a squared congruent to 15 modulo 16 is impossible. If u is even and v is odd, it follows that classes 1 and 9 remain possible, excluding 5 and 13. Thus, the negative sign case rules out classes 3, 5, 7, 11, 13, and 15. Summing up, case 1 excludes classes 3, 5, 11, and 13. Case 2, adding the equation gives p times a raised to the fourth plus 4 times b raised to the fourth equals x squared. We first factor the equation, and then a coprimality analysis shows that these factors are coprime. Then each factor is either a fourth power or p times a fourth power, where u and v are odd. Subtracting this equation gives u raised to the fourth minus p times v raised to the fourth equals plus minus 4 times b squared. The negative sign case gives u raised to the fourth plus 4 times b squared equals p times v raised to the fourth. Since u and v are coprime, it follows that u, b, and p are coprime too. Hence, p divides the sum of two coprime squares, so p must be of the form 4n plus 1. Therefore, classes 3, 7, 11, and 15 are excluded. But we can push the analysis further on the remaining classes 1, 5, 9, and 13. If b is even, this forces p to be congruent to 1 modulo 16, excluding classes 5, 9, and 13. If b is odd, this forces p to be congruent to 5 modulo 16, and excluding classes 1, 5, and 13. Summing up, the negative sign case rules out classes 3, 7, 9, 11, 13, and 15, while remaining available classes 1 and 5 according to parity. The positive sign case gives u raised to the fourth minus p times v raised to the fourth equals 4 times v squared, which has the same shape as the original equation, but with a different parity structure. This is precisely the case previously analyzed with x and y odd and z even, where the classes 3, 5, 7, 9, 11, 13, and 15 were excluded. Summing up, case 2 excludes classes 3, 7, 9, 11, 13, and 15. The following table summarizes the excluded and remaining congruence classes in the three cases. Common residues are 3, 11, and 13, thus matching Mordell's results. To end, we recover this solution using the previous argument. Assume a minimal solution with x, y, and z coprime. We focus our analysis on the parity structure x and z odd and y even. Then we factor and have the 16 times 37 times y sub 1 raised to the fourth equals x squared minus z times x squared plus z, where 2 and 8 divide the factors, since 4 dividing each factor can be ruled out. Given that x and z are coprime, then the factors divided by 2 are coprime too, as follows from the sum and difference. Therefore, the factors must either be a fourth power or 37 times a fourth power. Combining these equations, we find that 37 times a raised to the fourth plus 4 times b raised to the fourth equals x squared, and that 37 times a raised to the fourth minus 4 times b raised to the fourth equals z. We focus on the first equation, and after factorization, we find that those factors are odd and coprime. Hence, each one is a fourth power or 37 times a fourth power, with u and v odd. This gives this other set of equations, u raised to the fourth minus 37 times v raised to the fourth equals plus minus 4 times b squared, and u raised to the fourth plus 37 times v raised to the fourth over 2 equals x. The negative sign case for the first equation shows that u raised to the fourth plus the square of 2 times b equals 37 times v raised to the fourth. Here, 37 must divide a sum of coprime squares. Actually, Fermat's little theorem states that m raised to 37 minus 1 is congruent to 1 modulo 37 when m and 37 are coprime. The smallest m is 2, so we have 2 raised to 18 is congruent to plus minus 1. We check 2 raised to 18 is congruent to minus 1, and find that 2 raised to the 9th power is congruent to minus 6. Hence, 6 squared is congruent to minus 1 modulo 37. In fact, 6 squared plus 1 equals 37. Therefore, we have the trivial solution 1 raised to the fourth plus the square of 2 times 3 equals 37 times 1 raised to the fourth. Hence, we have that b equals plus minus 3, and u equals v, which equals plus minus 1. Then we substitute these values in the previous equations. X equals 19. We plug that into the first equation. Solving this equation, we find that a equals plus minus 1 as their integer solutions. Finally, we have that z equals minus 287, thus reaching the non-trivial solution. 19 raised to the fourth minus 37 times 6 raised to the fourth equals the square of 287. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. Your support means a lot.